So far, we've explored how the first derivative helps us figure out where a function is increasing or decreasing and where it reaches local maximums and minimums. But today, we're going a level deeper, literally. Have you ever looked at a roller coaster and noticed how some parts of the track curve upwards and some curve downwards? This is exactly what we're going to explore today, the idea of concavity. But what does concavity really mean? Imagine you're walking along a hill. If the slope is increasing as you move forward, the ground feels like it's curving upwards. That's called concave up. It's like holding a bowl upright. It could hold water. On the flip side, if the slope is decreasing, the ground curves downwards. This is concave down, like flipping that bowl upside down. Now, how do we figure this out mathematically? That's where the second derivative comes in. If the first derivative tells us about the slope, the second derivative tells us whether that slope is increasing or decreasing. Let's start by looking at some examples and see how the graph's shape reveals itself through the second derivative. Here's one last example, and I'd like you to try this one on your own by pausing the video and going ahead and giving it a try. You're going to use the exact same process that we used in the last question. Find the x-intercepts, use the first derivative to find the critical values, then the critical points, and then find the second derivative, use the second derivative test for concavity, and then graph it out. Pause the video for a second, and then when you come back, I'm going to show you the answer. So this is what this graph is partially looking like. I just realized I didn't actually finish it. So we have, let me just finish this quickly. So I've gone ahead and I have found my critical points. I found the coordinates for the critical points. I used my second derivative test to find if there was an inflection point. I looked at my concavity, and then I went ahead and started graphing it and didn't end up graphing it, the whole thing. So let's just go ahead and finish this. So I know that at 1.5, which is right here, I have an inflection point, which means that it's going to do a little wiggly woo here. That's the official physicsy term, is a wiggly woo. And it's going to come up, and then it's going to go back down in that direction. If you have any questions about that, pause the video here, go through the process. If there was something that you didn't quite get right on that one, go through the process. Feel free to email me if you want to. I'd like you to go ahead and do the homework questions. They are really good practice because as we get going with this, these are fairly simple functions to be able to take the derivative of and use these tests. The functions are going to get a little more complex, so I want to make sure that we've got these concepts cemented on how to use first and second derivative tests to graph something, so that when we move on to harder functions, we're able to do it more easily. And I will post more practice questions for tomorrow's lesson so that you will get even more time to practice. Take a look at this graph. I want you to pause the video and try to sketch the derivative, just knowing what we know about points on the parent function versus where they'll be on the derivative. Was your graph of the derivative relatively close to this one? What points were easy to identify and what points weren't so much? The zeros are pretty easy. That's where the slope of the tangent equals 0 on the original function. If we pop back over to this one, we can see that that's going to be wherever it turns around. So we're going to have zeros for our derivative right at those 2 points. And you can see I've filled them in on here already. We can also see what the slope of the tangent's going to be doing. So prior to this point right here, the slope is actually decreasing or is negative. So that explains why this is going that direction. Once we get to that point down here though, the graph actually turns around and the slope becomes positive in this direction again, which is why now we're seeing this. Again, over here, slope is positive, so it will be going up in that direction. Slope is negative, will be going down in that direction. What about the vertex of the derivative? Were you close with where you placed it? We know that it will lie somewhere on the x-axis where x equals 0, but where exactly? We could try to take the slope of the derivative, or we could try and take the slope of the original function right there where x equals 0, but hand drawing that can be quite tricky, and we've seen that that can be quite tricky. We could use Desmos, but what if we looked at it algebraically? We can create an equation for the original function using the zeros and a point somewhere on the graph. Let's use our maximum, which let's say is 1 and 6. So let's create an equation. So if y is equal to ax times x minus 2, these are my zeros, x plus 2, and this is a third degree polynomial, so I'm going to have to end up with an x cubed somewhere. So let's just expand this out. That gives me x squared plus 2x minus 2x minus 4. Now I'm going to distribute, collect like terms, and then I'll distribute that x to inside the bracket. So I end up with a times x cubed minus 4x. Okay, now we need to solve for x by subbing in our point at 1, 6. So y equals 6 when x equals 1 cubed minus 4 times 1. So a will end up being negative 2. Now we can create the equation, or write the equation for the original function. So for the original function, f of x is equal to negative 2x cubed plus 8x. We can find the equation of the derivative by, no surprise here, taking the derivative. We're going to use the power rule. So use the power rule, and let's get the first derivative. So my first derivative is going to be equal to, so I'm going to use power rule and take this 3, the power, and bring it down. 3 times negative 2 is negative 6, and 3 minus 1 is 2. Derivative of 8x is just 8. So my first derivative will be negative 6x squared plus 8. We can use this equation to find the vertex, since we know it's going to be where the value of x is equal to 0. So let's substitute 0 in, and I think we can see that it's going to be 8. So my vertex is going to be at 0, 8. And indeed, we really already knew that just from looking at the graph. Now let's sketch the derivative of the derivative. So the second derivative, like when we looked at our position time versus our velocity time versus our acceleration time. The slope is zero at the vertex. So we've already got that point on here. I've got so many colors going on. I'm going to erase just a little bit here. So let's just get rid of some of this that's happening. Okay, so now let's put this one in green. So I know right here that the slope is 0 at the vertex. So my vertex here of my derivative, that's where my slope will be 0 on my second derivative. Looking at the graph of the derivative now, we can see that the slope is positive, that we have slope in the positive quarter, okay, but it is decreasing. And then we have slope going down this way. So derivative of a quadratic we know is a straight line. So let's look at the derivative of the graph and see. I'm not going to start over again. I'm just going to keep going. Looking at the graph of the derivative, we can see that the slope is positive up to x equals 0 and negative after x equals 0. Can you see a connection between the slope of the second derivative and the direction the original function is opening up? What about where the second derivative equals 0? So right here, what do we think is happening there? Here's the graph of all three functions. Now let's get an equation for the second derivative. So my first derivative, f of x, was equal to negative 2x cubed plus 8x my first derivative then was equal to negative 6x squared plus 8. So what is my equation for my second derivative going to be? I'm just going to use the power and the constant rule again to figure it out. So the derivative of negative 6x squared is negative 12x, and the derivative of 8 is 0. So we can see that we have the second derivative is equal to negative 12x, and it is indeed a straight line. The first derivative is equal to negative 6x squared plus 8. And here's our original function, which was equal to negative 2x cubed plus 8. Looking at the graph, we can see that the second derivative passes through 0, 0. Notice that this appears to be where the graph is changing direction. We've got an increasing slope to this point, decreasing slope after this point. The second derivative can help us determine where a graph changes direction. This is called the point of inflection. It can also tell us the concavity, or the direction of opening, for the local max and min. I'd like you to pause the video again and try the Desmos activity posted for this lesson. It's going to introduce you to the concept of concavity and how it relates to the second derivative. Now that you've seen what concavity looks like in the Desmos activity, let's look at it a little more closely. Here are graphs for two functions f and g. Each increases as they move from point A to point B. So as we're moving from point A to point B, both of these functions are increasing, but they're bending in different directions. Graph f lies above its tangent line. So if I were to draw tangents anywhere along here to touch points, we can see that that total function f is above the tangent line. This is called concave upward, or it can hold the water, or it's the smiley face. Graph g lies below its tangent lines. So anywhere I were to draw a tangent along g, the function will be below the tangent line. This is concave downward, or the frowny face, or the water will dump out. Let's compare the change in slopes of the tangents for f and g. So for g, what's happening to the slope as we go from A to B? Well, the slope is increasing as we go from A to B. So we say the slope is increasing. And what's happening to function f? As we go from A to B, the slope is decreasing. We've seen that if a function is concave upward, then the slopes are increasing. The slopes are represented by the derivative. If a function is increasing, then the derivative will be greater than 0. So this is represented right here. If I have a derivative where the slope is, a function where it's concave upward, then the slope is increasing, or the slope of the derivative, that's this part right here, will be greater than 0. So the derivative of the derivative will also be greater than 0. So the second derivative will also be greater than 0. Similarly, if the curve is concave downward, so now this one, the slopes are decreasing. So the slope of my derivative is decreasing, or less than 0. So the derivative of the derivative, my second derivative, is also less than 0. What happens if the second derivative equals 0? If the second derivative is equal to 0, then the derivative has a possible turning point when x equals c, and c is just the x value where the slope of the second derivative is 0. This means that the original function has a possible inflection point where x equals c. We can use the second derivative test for local extrema to determine if this point actually is an inflection point. So the second derivative test tells us that if the first derivative at c is equal to 0 and the second derivative at c is less than 1 or negative, then the original function f at x has a local maximum at x equals c. If the first derivative is equal to 0 at point C and the second derivative at C is greater than 0 or positive, then f at x has a local minimum when x equals c. So let's try an example. We're going to sketch 3x to the power of 5 minus 5x cubed by finding all the x-intercepts, the local maximum, the minimum points, and the inflection points. I've written it out. I've given us a bit more room here because we're going to need it. So let's start with the x-intercepts. So for my original equation, where y equals 3x to the power of 5 minus 5x cubed, the x-intercepts are just going to be where this equation is equal to 0. 0 is equal to 3x to the power of 5 minus 5x cubed. Now, I need to get this into a form that's going to allow me to know what my intercepts are. So I'm going to pull out a greatest common factor of x to the power of 3. Inside the brackets, that leaves me with 3x squared minus 5. Now I know that I will have an intercept when x equals 0, and I will also have an intercept when x is equal to plus or minus the root of 5 over 3, which for what we're doing here, we're going to say is approximately equal to plus or minus 1.3. So those are going to be my 3 intercepts that fall along the x-axis. Now let's see what of those might be local maxima and minimum, and we're going to use the first derivative test to find those critical points. So using the first derivative test, we're going to take the first derivative. So if f of x is equal to 3x to the power of 5 minus 5x cubed, then my first derivative will be equal to, just using the power rule, the derivative of 3x to the power of 5 is 15x to the power of 4, and the derivative of negative 5x cubed is equal to 15x squared. So now we have our derivative. We're going to find the critical points, and the critical points, or the critical numbers here, are going to be where f prime at x is equal to 0. So same thing that we did up here, only now for the derivative. We're going to set the derivative equal to 0, 15x to the power of 4 minus 15x squared. I can pull out a greatest common factor of 15x squared this time. That leaves me with x squared minus 1. This is a perfect square. So I end up with 15x squared, x plus 1, x minus 1, which gives me critical points when x is equal to 0, when x is equal to negative 1, and when x is equal to positive 1. So now I need to turn these critical numbers into the critical points and find the coordinates on the original equation, and I'm going to do that by plugging these values back into the original equation, which was 3x to the power of 5 minus 5x cubed. So I think we can see that when x is equal to 0, so when f is at 0, 3 times 0 is going to be 0, 5 times 0 is going to be 0. So we're going to end up with a point at 0, 0. We're going to repeat that for when f is at negative 1. And when f is at negative 1, we have 3 times negative 1 to the power of 5 minus 5 times negative 1 to the power of 3. That actually gives us 2. So we have another critical point at negative 1 and 2. And then finally, when when x is equal to 1, so f at 1, 3 times 1 to the power of 5 minus 5 times 1 to the power of 3 is going to give us negative 2 this time. So now I have another critical point at 1 and negative 2. Okay, now we need to figure out what's happening around those points. whether they're maxima, minima, or whether or not it's a point of inflection. And that's where we're going to use our second derivative test. So I'm just going to pop up over here, and now we're going to use this second derivative test. Okay, so remember the second derivative is just the derivative of the derivative. So if I have f of x is equal to 3x to the power of 5 minus 5x cubed, my first derivative for that was equal to 15x to the power of 4 minus 15x squared. Now I'm going to take the derivative of the derivative to get the second derivative, and the process is exactly the same. Using the power rule, the derivative of 15x to the power of 4 equals 60x cubed. And the derivative of minus 15x squared becomes minus 30x. Again, I can pull a greatest common. So now, sorry, I'm going to back it up a step. So this is going to let me know, I'm going to do the concavity test. And the concavity test tells me that when my second derivative is equal to 0, that's where I'm going to know if I have concavity. So I'm going to set this derivative, my second derivative, equal to 0. 60x cubed minus 30x. I can pull out a greatest common factor out of there, actually this time of 30x, and I am left with 2x squared minus 1. This tells me that there is something going on at x equals 0. And my other points of interest will be plus or minus the root of 1/2. And the root of 1/2 is approximately 0.707. So now we're going to set up our table to figure out what the concavity is doing at those particular points. So I'm going to set it up. I feel like I'm using an awful lot of red on this page, but so what is my second derivative doing at a point where x is less than negative root of 1/2? What is the second derivative doing when x is equal to 0? And what is the second derivative doing when x is greater than negative root of 1/2? That's what we want to know. Then we're going to compare that to what our actual graph is going to be doing, the concavity of the graph. So we're going to pick a point. To do this, we need to know if these are greater than 0 or less than 0 or equal to 0. These in here. So we are going to, fill that back in. Okay, so we're going to choose points on either side. So for this one here, I'm just going to choose when x equals negative 1. That's less than the root of negative 1/2. So let's just pop this down here and let's just work it out. So when x is equal to negative 1, then I have 60 times negative 1 cubed minus 30 times negative 1, and that gives me a value of negative 30. So my second derivative test is telling me that this is negative here, or if we wanted to say it is less than 0. That means that my graph, my original graph for my function, will be concave down. Remember, if I have a second derivative less than 0, it will be concave down. So it's going to be the frowny face. When x equals 0, here my second derivative also equals 0. So when x is equal to 0, the second derivative at 0 is also equal to 0. So remember we said when the second derivative is 0, this will be a point of inflection. A point of inflection. And it's going to look it's going to change direction. So it might look like that. We'll be able to figure it out once we see once we start to graph it. And then the last one we want to do is we want to look for a point that's bigger than 1/2. That's positive 1/2, not negative 1/2. And so I'm just going to choose a point. Doesn't really matter. I'm going to choose x equals 1. So when x equals 1, plug that in. So 60 times 1 cubed minus 30 times 1 is going to give us positive 30. So this is positive, which means that x is greater than 0, which tells me that this is going to concave up. So at this point, it's going to look like this. So now let's put this all together and let's graph what this is going to look like. And hopefully I've left myself a little bit of space here. Okay, so I'm going to draw some coordinates here. And I want to spread things out a little bit because our points are fairly close together. So I'm going to make that, let's make that 1. And let's make that 2. 1, 2, 1, 2, 1, 2. So now, let's start by adding the x-intercepts. So our x-intercepts, remember, were at, when x was negative 1.3, when x was at negative 1.3, so let's put that right about there. We know we have something happening at 0, 0, and at positive 1.3. Okay, so there's my x-intercepts. Now let's add our critical points. So our critical points over here, we found 3 of them, 0, 0, negative 1, 2, and 1, negative 2. Oh, excuse me. So we already have 0, 0 on here. Now we have to do negative 1 and positive 2. It's going to be up here. And then we have 1 and negative 2. Now let's use our concavity to see what's happening. So I know at this point here, coming up to this point, it is concave down. That's what this is telling me, is that this is concave down. Then when we come over on the other side, I know that this is going to be concave up. So now we just need to figure out what's actually happening in this area here. And I'm just going to undo a little bit of that there. I've got to work quickly because my iPad is about to die. And I want to get this done. So we want to know what's happening right before there. And this is an inflection point. So we know that this is a point of inflection, which means this is where it's going to change direction. So it's going to flatten out and then come down this way. And so there is our generalized graph of what this is going to look like using our x-intercepts, our first derivative to find the critical points, and our second derivative to find the inflection points. Here's one last example, and I'd like you to try this one on your own by pausing the video and going ahead and giving it a try. You're going to use the exact same process that we used in the last question. Find the x-intercepts, use the first derivative to find the critical values, then the critical points, and then find the second derivative, use the second derivative test for concavity, and then graph it out. Pause the video for a second, and then when you come back, I'm going to show you the answer. So this is what this graph is partially looking like. I just realized I didn't actually finish it. So we have, let me just finish this quickly. So I've gone ahead and I have found my critical points. I found the coordinates for the critical points. I used my second derivative test to find if there was an inflection point. I looked at my concavity, and then I went ahead and started graphing it and didn't end up graphing it, the whole thing. So let's just go ahead and finish this. So I know that at 1.5, which is right here, I have an inflection point, which means that it's going to do a little wiggly woo here. That's the official physicsy term, is a wiggly woo. And it's going to come up, and then it's going to go back down in that direction. If you have any questions about that, pause the video here, go through the process. If there was something that you didn't quite get right on that one, go through the process. Feel free to email me if you want to. I'd like you to go ahead and do the homework questions. They are really good practice because as we get going with this, these are fairly simple functions to be able to take the derivative of and use these tests. The functions are going to get a little more complex, so I want to make sure that we've got these concepts cemented on how to use first and second derivative tests to graph something, so that when we move on to harder functions, we're able to do it more easily. And I will post more practice questions for tomorrow's lesson so that you will get even more time to practice.